Welcome to EEE 316 Power Electronics project presentation. The title of our project is to make a stepper motor driver using a microcontroller. Here is the simulating diagram for our project. We have implemented a unipolar stepper motor driving circuit where the gate pulses are being generated by a MATLAB function. The circuit has two parts, the Simscape electrical and mechanical part and the coding part. First, let's take a look at the power circuit. We are using a 5-terminal unipolar stepper motor with a four-step size of 1.8 degrees. The four terminals are connected to 4N MOSFETs and the common terminal of the coils is connected to a power supply. The MOSFETs are driven using appropriate gate pulses from the MATLAB function and their voltages are shown here. The capacitors and resistances are connected to smooth the voltage impulses and to introduce non-ideality into the system to allow simulating to run properly. On the mechanical side, the motor rotation is sensed using a motion sensor and is shown in this scope, which will allow us to measure the movement of the motor shaft.
Hello, we are going to explain the MATLAB function with which we are generating the gate pulses for our MOSFETs. Here the first input is the clock, which tells our function what time it is currently. Here we can set the step limit after which the motor will stop. Here we can set the speed of the motor in rotation per minutes. Here in this block, with this switch, we can select one of two modes. Continuous mode means the motor will run indefinitely until we press the stop button, or it will take the counted mode. It will take the limited number of steps set in this box. We can select another mode here from three options. One is full step, one is wave drive mode, two is full step mode, and three is half step mode. And here we can set the direction, whether the motor will rotate clockwise or anti-clockwise. And here we have a start and stop button. Here we have a feedback which we will understand when we look inside the code. Here we're taking, these are the inputs that we are taking from the function, taking from the blocks, and here is the prev. These matrices is the feedback input. Here we are taking some values from the previous run of the function. For example, one is t prev, which is the time that the last step was taken. If we compare it to the present time, we can know when to take the next step. We are retrieving some important parameters from the prev matrix here, and here we are counting the time period, step size from the mode and set speed. This little box transition, it means that when suddenly a change of mode takes place. For example, the motor was running in wave drive mode and we suddenly change it to half step or full step mode. Then the motor will reset its step count and some other important necessary parameters, and then proceed accordingly. Here we have a state matrix. We have listed all the possible gate pulses here. There are eight pulses. If we take a look at the row 1, 3, 5, and 7, we can see that these are the gate pulses for the wave drive mode. Similarly, row 1, row 2, row 4, row 6, and row 8. These are necessary for the full step mode, and all the 8 rows are necessary for our half step mode. Here we have come to the main body of the code. Here, depending on which mode the motor is running on, we will know which row to execute after which row. For example, in wave drive mode, it goes from 1 to 3 to 5 to 7 if it is in forward mode, and from 7 to 5 to 3 to 1 if it is in reverse mode. We are multiplying it by 5, so because we need at least 5 volts to operate our the 4 MOSFETs, and we are storing the current values in the matrix prev and sending it in our feedback. That is all we are doing in our function.
Let's see the simulation in action. First, setting the control in half step mode and continuous rotation in forward direction. We can see that the motor is continuously rotating at discrete step. Pausing the simulation, if we measure the step angle, we can see that the step angle is around 0.9 degrees. And in case of gate pulses, the firing angle sequence exactly following the sequence of half step mode, and the sequence is A, B, B, C, C, D, and D before going back to A. After that, we will change the mode from half step to full step mode. And after changing the mode to full step, we can see that immediately the step angle gets doubled, and now the current step angle is around 1.8 degrees. With the changes of step angle, gate pulse sequence also changed. Now the current gate pulse sequence is AB, BC, CD, DA before going back to AB. Finally, we will check the motor for wave drive mode. If we change the mode from full step to wave drive mode, we can see that the step angle hasn't changed, but the gate pulses sequence changed this time. Now, if you look at the gate pulses, we can see that current gate pulse sequence is simply A, B, C, and D, which is exactly following the firing angle sequence for wave drive mode. After checking three basic type of controlling, now we will check the motor in backward rotation. After changing the rotation from forward to backward, immediately we can see that now the step angle is started to going down, as well as the gate pulses sequence also reversed immediately. Now the current gate pulse sequence is opposite from the previous one, and which is D, C, B, and A. Now we will check the backward direction mode for other controlling mode also.
Now let's see backwards spin in other modes. Firstly, in full step. Now in half step. Now it is time to control the speed of the motor. Increasing the speed knob, we can see the slope of the motor becomes steep as well as being smoother. And the frequency of the gate pulses increases as well. However, if the speed or the frequency of the gate pulses increase so much that the mechanical shaft can't follow it, the motor will vibrate instead of stepping continuously. Now we will decrease the speed and check discrete stepping mode. In discrete stepping mode, the motor will rotate only the amount specified by the control knob. Let's set the control to 10 steps. As it is already set in 10 steps, we can see the motor is currently at a stop. As soon as we start, the motor has rotated exactly 10 steps, setting the direction backward. Once again, the motor has rotated 10 steps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Before online classes, we managed to implement a bipolar stepper motor driving mechanism by creating two H bridges using RF-Z44N MOSFETs. A standard NEMA 23 bipolar motor has two coils instead of four like the unipolar ones. Also, they require the coils to be energized in reverse directions, which is achieved using the H bridges. In this video, the motor is rotating in half-step mode, and the appropriate gate pulses are being generated from the Arduino microcontroller. And here is a schematic diagram of our physical circuit. That's all for our presentation. Thank you for your time and attention.